All right. Good afternoon, you guys. Today we will be continuing our conversation on pipelining structures, pipelining processors. This is your third and last part of the pipeline series. Today we'll be focusing on the load use data hazard, which is a type of data hazard that we cannot fix with the forwarding, register forwarding. So we'll take a look at how we what this data hazard is and how do we go about fixing this hazard, and we'll also talk about what happens in terms of branching instructions. So we'll also talk about some other type of hazard as well. So just to recap quickly, hazards are conditions in which you cannot execute the next instruction because you don't have the correct results ready, right? So it cannot be executed correctly in the next clock cycle in the pipeline. Those are hazards, and we talked about the three different types. And so far we've been kind of focusing on the data hazard mostly in the last class. We tried to fix that using the register forwarding technique. So the data hazard was when the instructions are attempting to use an item before it is ready, right? So I can for example, if the destination of an add instruction is a particular register, say S1, and we are reading that S1 right in the second instruction, the next instruction, then we may not have the contents of S1 ready for the second instruction to get executed correctly. So we looked at data hazard. How can you fix it using stalling maybe, or register forwarding. Today we are going to look at one special case of data hazard, which is the load use hazard, and we'll also talk about control hazard today. So control hazard is a hazard which happens because of a decision to be made. The attempt to make a decision before the condition is evaluated, because things are in a pipeline, right? Things are getting executed. So even before you make a decision, how can you start working on an instruction? So there are a few interesting ideas regarding that. We'll talk about that. So this was to this structure in which you have your 5 stages, right? The instruction memory over here, the register file over here, the execute stage, the ALU, the memory access with the data memory, and then there is a mux for the write back stage. All these 5 stages of the instruction life cycle are laid out over here with the pipeline registers right in the middle. So you've got first pipeline register there, second, third, and fourth between each of those stages. Now in the last class we focused over here, right? So we were talking about how can you implement a forwarding unit which essentially takes the information of which register are you trying to use as destination in one stage, and then does it match the source registers, one of the source registers for the second instruction right next to it, following that. So depending on that, we were able to either do a XMEM forwarding or MEM write back forwarding. Essentially the idea is if things are getting things are ready right after the ALU, we will try to forward that content instead of waiting for later stages, right? So that was what forwarding was. But these ideas were specifically for a condition in which we are trying to write to a register and then following that up with a read, right? This is also called write use, meaning you're trying to write to a particular register and reading the same register right in the next instruction. So that is your write read hazard, or also called as the write use hazard, and that can be fixed using this forwarding unit. But there is a special type of write use case, which is a load use situation, which cannot be solved by a forwarding unit. So all the things that you are seeing in terms of yellow are the ideas that we talked about in the previous lecture. So the goal over here is to see why can't we always do the forwarding, right? So it doesn't work for the load use data hazard case. So let's talk about that. Forwarding is only going to work if the stage that really needs the value is later in time. So if we look at the add instruction, right? So suppose instead of this load word, we had an add instruction, and we were trying to write something to the second register, right? Some other registers are functioning as source, but if we are trying to write to a $2 in the first instruction instead of load word, and right in the second instruction we are using the same register, right? So that was a problem. That was what we tried to fix in the last time. But the thing to note here is, when is this ready? When is the content to be written on $2 ready? Well, if you are doing an add instruction, then it is ready right here, right? So as soon as you get done with the ALU, you have the contents to be written on $2, which means that you could forward that, right? So things could be forwarded because of that situation. Now, what if instead of add, you have a load word? Well, load word instruction, you are actually ready with the contents to be loaded into register 2 in this case over here after you read the data memory. So you are not going to be able to forward that anymore, right? So because you have to go back here, you cannot do that because time has already passed. So what can you do? There are some other techniques that we need to come up with to solve this load use data hazard. So, I want to spend a few moments discussing the difference between the kind of hazards we talked about in the last class to the kind of hazard that we are trying to fix in this lecture, right? So in add, things were ready over here, so we could forward. But in load, things are not ready over here. Things are actually ready over here. So we cannot forward anymore. It actually has to go back. So we need so that's the problem. That's what we are trying to fix. Questions here as I hope you guys see that the problem is I'm trying to load something into $2, and right in the next instruction, I'm using that same register. So in one case, the data is ready here, right? So load new data. So that data is ready after you read the data memory. But when do you actually need this over here? So this is the problem. When do you actually need it? You actually need it right here. So clearly this needs to go back. That's a problem, hence highlighted in red. However, if you notice, we are also using $2 here as an operand, but that's not a problem. We could do that, right? Things are ready over here. We could forward and we could forward. So forwarding will take care of that, those two scenarios, and we should be fine with the forwarding unit. The only problem comes because of this guy, right? So we cannot fix this with the forwarding unit. All right. Questions here? So maybe I can say add was ready here. Add result ready here. So we could forward. All right. So that type of data hazard is called the load use hazard. I'm trying to load something into a register, and right away I'm trying to use the same register. That is a problem. So let's try to see what we can do. Well, we can obviously stall, right? So we can clearly delay things and we can work around this situation. Now, when do you stall? Let's see. First, we would need to check, do we have a load instruction in the execute state or not, right? So here we have a load instruction in the execute stage over here. If your load word is the instruction that you are working on, then this particular situation is possible. If you don't have a load word instruction, then you don't have to worry about this load use data hazard possibility. So the first question is, do we have a load word instruction in the execute stage or not? And if yes, does the destination of the load word, $2 in our example, match the one of the source registers of the instruction in the instruction decode stage, which means one stage earlier, which happens for the instruction that is right after the load word instruction. So in our case, this particular destination register was $2, and one of the source registers was also $2. So if I go back and take a look at the pipeline diagram here, I have a load word in the execution stage right here, and the source registers, one of the source registers that is in the instruction decode stage, trying to read the register file, is also the same $2. One of the source register is $2. So that's the only situation in which this can happen. This load use data hazard can happen. And if that is the case, stall the pipeline. Now let's see how many cycles do we need to stall the pipeline for. So in terms of hardware, in terms of a combinational circuit that we need to design to do this check, that combinational circuit is going to be checking for this. If your IDEX memory read, what does that mean? You remember in load word, for load word, this would be a 1, right? For load word instruction, the instruction that is in the IDEX pipeline buffer, the value in the IDEX pipeline buffer for this particular field, memory read, is going to be 1. For load word instruction, memory read is 1. Do you guys agree with that? Because we are trying to read from memory and load things into a particular register. So if an instruction, see, the load word instruction goes through the fetch, decode, and then after the decode, it is going to write something to these pipeline registers, right? So this is IDEX. What is it going to write? It is going to write a bunch of values, but it's also going to put on some control signals over there. For example, the memory read. So if I can go back here, I can see this, right? So in the instruction, this is your instruction decode stage, ID stage, and this is the EX stage. So in the instruction decode stage, it is going to take in the most significant 6 bits of the instruction, 6 MSBs, and depending on that opcode, it is going to generate control signals. One of the control signals is the memory read, which goes on this pipeline register and this pipeline register, because it is going to be used here, right? Memory read is here. Along with memwrite. So if it's how do we detect whether we are working on a load word instruction or not? Well, take a look at what you have decoded here. If the IDEX pipeline register, the memread field for this particular pipeline register is 1, that means you are trying to read from memory, which happens in the load word instruction. So all of this is to suggest you are working on a load word instruction. And what? So we have taken care of this guy, right? The first condition. And what? We need to check for the destination register in the load matches the source register in the instruction previous to that. So the destination register in the load is what? IDEX register RT. So that is one of the destination registers. Does that match? So this is your destination of load. Does that match source? In this case, we are just checking for RS, and you have another statement just below that checking for RT. Source of next instruction. In our example, what was it? If I go back, it was AND, right? So it was AND. So I can just say in our example, it was AND. So if the destination of load matches the source of the next instruction, or this, and this could be RS or it could be RT, right? So it doesn't matter which operand, RS or RT is fine. So that's where we are checking the second condition. If these two, this and this, right? So this and this. If this and this are satisfied, then we need to figure out how to stall the pipeline. So detecting the load, how do you detect load use hazard? If the load is in the execution stage, that is, if the IDEX pipeline register and the field is memoried is 1 and the load destination is the same as the source of the next instruction. If those two conditions are met, then we have detected the load use hazard. So clearly there is a problem here. Destination matches the source. We have a problem. So for which of these conditions is the problem and for which of them it is not the problem, right? So if you see this, things are ready over here. I need them here. So I have a problem there, and I also have a problem. I may not have a problem here. I could get away with this because it is happening after, right? So one instruction I definitely have to worry about. But then if you have this guy, then so the solution is I need to stall. So let's see how much I need to stall. So I'm going to build a hazard detection unit for that. The hazard detection unit is essentially going to check for the load use hazard. When does that load use hazard occur? For that, what all information do I need? I clearly need to see whether I am working on a load word instruction or not. That information, where do I get it from? I get it from the IDEX pipeline register, and it is functioning as an input to my hazard detection unit. Note that the register forwarding unit is also there. It still exists in our pipeline, in our data path. We have just added another unit to do a special detection for the load use hazard. So it is taking in an input from the IDEX pipeline register that tells me what is memoried, is it 1 or not. If it is 1, I know we are loading. And it also takes in 2 more values. Those 2 values are coming from the instruction. And we are essentially trying to see whether or not the destination of the load is the same as the source in the next instruction. So if this is 1 and these 2 are matching, then we are going to, well, those 2 are, there is 1 there, but we also have 1 from here. So in our case, this was the load word, right, destination. does that match and source, right? In our example, it was and. So we are checking whether the destination register for the load word, does it match the destination register or source register from the AND, one for RS, one for RT, could be either operand. So all of those things are functioning as the input to my data hazard load use hazard detection unit. What are the outputs? Well, I have an output connected to a MUX here, and I have an output connected to the IFID pipeline register, and I'm controlling whether to write or not. And I'm also controlling whether to write or not for the program counter. So essentially, this is what I'm going to do. If I detect that this is 1, I am loading. And if I detect that these two are matching, the load word destination and one of the source of the next instruction is matching, then what I can do is this. I can make all my controls signals go to 1. If I make all my control signals go to 1, that is as if I am working on a NOP, no instruction. So I'm essentially stalling by using NOP. Stall using no operation, NOP. And for NOP, all you have to do is this particular control to the MUX makes this 0 go to all the control lines. So this 0 is essentially written everywhere. 0 here, 0 here, 0. So all the, if you guys remember, there are 9 entries in this, right? We did an activity based on that. So all 9 controls signals are zeros in that case, which is exactly how you would execute a no operation. That's a NOP. So detect this, and if this is satisfied, then you push a 0 to all your controls. And also, don't write over here. Set these signals so that you don't write, because you don't want your program counter to get updated. You don't want your IFID to be written by the new instruction that you're trying to decode, right? So you are essentially stalling by working on a no operation, and the no operation is being executed. No operation is essentially pushed into the pipeline by not updating the program counter and pushing a 0 for all your control signals. Do you guys see that? So that's your hazard detection unit. Checks for the condition that we listed over here, and if it is satisfied, then it is going to stall the pipeline by not updating the program counter, but instead pushing zeros to all the control lines. So let's take a couple of minutes to see if you have any questions here or not, and then we can move forward. See, by doing this, we are making sure that all the registers or memory is not being written. All right. Now, whenever we use a stall by inserting NOPs, we are going to slow things down, right? Let's see, there's a question in the chat box. Will the hazard unit only deal with NOPs? The hazard unit will either make the next instruction a no operation, or if no load use hazard is detected, things will go as is, right? So PC would be updated and it would decode and stuff. So the hazard unit is responsible to either make the next operation not or continue as usual. So it is making the next operation not if it detects it. All right, so the stalling, while you're doing the stalling, you're essentially saying that my pipeline doesn't have any useful instruction to work on, which also means that things are going to get slowed down, right? So that's not going to be your fastest response time. Your throughput is going to go down. So another alternative is to reorder the code, and we'll see examples in today's class where you can reorder without affecting your complete program. So the compiler can look to reorder the code. The compiler can look into reordering the code, which is following a load instruction, so that the next instruction becomes independent of that load, right? So for example, if I go and look at things over here, let's see, can I do some reordering over here? So instead of load word, can you guys think of some option over here which will execute the same program by simply reordering the code? Move SLT up. That's right. So if I move SLT way over here instead of and everything is pushed down by 1, I'm done, right? SLT, where is and is that? Yeah, that's right, right? So by simply moving this up, I have reordered the code. Everything is going to take the same amount of time, but I don't have to worry about this load use data hazard. So the compiler can help you do that. However, it is going to increase the complexity of your design. So now you're going to have a typical trade-off between hardware complexity, because you are going to have to check which instruction you can actually reorder. So you're going to have like more hardware to do those checks. Hardware complexity goes up, and also compiler decision also takes more complexity in terms of software. So now you have a trade-off. Okay, do I want more hardware complexity or software complexity? But this particular case is called a delayed load, which means that until I have the load word ready, I'm not going to work on an instruction which requires that correct loaded word in the register. So that's what we call a delayed load. Now let's see. Here is an example. Let's try to do that same kind of scenario here. Do you see a load use hazard present in this example? Let's number them so that we can discuss. This is 1, 2, 3, and 4. So those are instruction numbers. Do you see a load use hazard happening? And if yes, in which 2 instructions? Two and 3, right? So 2 and 3 have a problem. There is a load use hazard present over here. I am writing to $2 and I'm using $2 right in the 3rd instruction. So there is a load use hazard present over there. Now, can you guys think of fixing it by reordering the code? Which 2 instructions maybe can you change or reorder? Switch 3 and 4, right? So if you switch 3 and 4, you kind of don't have that situation anymore. So that load use hazard is removed, and nothing really happens to the pipeline. You don't have to make any adjustments. 3 and 4, you just switch. All right. So those were the ideas in terms of a new hazard detection unit. Now let's focus on the control hazard, which is a result of making decisions. So when you attempt to make a decision before the condition is evaluated, right? So think about the branch when equal instruction. When you are executing a branch when equal, you are comparing the results of one instruction, one register with the other register, and depending on whether they are equal or not, you are either going to the next instruction, or you are jumping to a branch destination. But because you are using a pipeline, you would have, before you actually evaluated that, you would have already started working on the next instruction, right? So you don't even know whether that is going to be helpful later on or not. That kind of a situation is what we are calling a control hazard, which is also known as the branch hazard. Before you evaluate the condition, you have made a decision. You have made a decision to work on the next instruction, which might be incorrect. Now let's try to take a look at where are we actually making that decision. So suppose you are this is the data path that we have been discussing so far, with all the control signals highlighted in blue and yellow. Now over here, let's try to see where is the branch, where is the condition evaluated. If you are working on a branch when equal instruction, where is the condition evaluated? Anyone? ALU 0, okay, so ALU 0 is going to give you one thing, but you are also going to need some other control signal, right? One of the control signals for the memory. So the branch condition is being evaluated right here. You see that? Which is essentially going back and controlling what is your PC source. So PC source, either the next one, PC plus 4, or the new branch instruction, right? But that is, the condition is evaluated over here in the memory access stage, in the memory, right? But by that time, some other instructions have already started working on things. One instruction, so if you are here, one instruction is here, here, and here. The other instruction is here and here. And the third instruction is here, right? So three other instructions below that branch have already, come into the pipeline, which we may not need to worry about them if the condition is false. So let's try to take a look at some of the things we could do here. This is the control hazard situation. We have a execution order over here where there's an add instruction followed by a branch when equal, and then followed by a load word instruction. So the add instruction takes up time from 0 nanoseconds all the way to 9, or actually 10 nanoseconds, right? If you consider both of them as 2 nanoseconds. So 2 nanoseconds for fetch, 2 for register access, 2 for ALU, 2 for data access, 2 for register writing. Now the branch when equal instruction is next in the pipeline. For the first 2 nanoseconds, it does nothing. For the next 2 nanoseconds, it does the fetch, register access, ALU, data access, and register writing. Now, if you take a look at what is the time for which there is nothing in the pipeline, if you just push out everything until you make that decision, where are you making the decision? You guys just said evaluate the decision in memory, right? So BEQ gets evaluated during data access stage. So until then, I don't even know whether I want to start working on the load word instruction or not. So suppose I stall things, suppose I delay things until my branch instruction is evaluated, that would mean I could have started working on load word here. Instead, I'm starting to work on load word here, right? So that would mean a 6 nanosecond stall because of this control hazard. The issue being, I don't know if you want to work on the load word instruction or whatever is present at this particular offset, right? So PC plus 4 plus this offset will give you a branch destination. So I don't know whether you want to work on load word or that branch destination until 10 nanoseconds. So stall. That's idea 1. Not a very elegant solution, but that's an ideal. That's our idea 1. Stall until the decision is made. What is the cost? The cost is 6 nanoseconds, which is essentially 3 cycles. 1 cycle per stage, right? So we said the clock cycle is limited by your slowest stage. In this case, it was 2 nanoseconds. So that's your 3 cycles, 6 nanoseconds penalty. Now, the next question is, can we do better? Can we start working on load word earlier? For that, we may have to be less conservative. Meaning, you might be risking on working on maybe the correct instruction or maybe an incorrect instruction. So if you are incorrect, then you have to walk your way back. So that's idea number 2, where you proceed assuming that the branch is not taken. So if you assume that the branch is not taken, which means that branch when equal stage has, it is not equal, right? So that means that the BEQ, you're not branching, right? Branch is not taken. So if your branch is not taken, then you start executing 44, 48, 52, and so on. So if that's your next idea. Just go on as if the branch is not taken. So you execute the branch instruction, then AND, then OR, then add, then load word. And note over here, this particular offset, here, how do you compute the branch destination? You compute the branch destination by adding PC plus 4 plus offset, right? And PC right now is 40. That's your current program counter. So 40 plus 4 plus the offset is 28. So we are assuming that the offset is already in bytes, assuming that in bytes. So this is offset assumed to be in bytes. Assumed to be in bytes. Because as you know, for branch instructions, the syntax is you have to provide the offset in words. So you would have to multiply it by 4. Right now, I'm just assuming that the offset is already in bytes, which is not consistent with the syntax of that instruction, but that just helps us see the branch destination here. So you take the 40 plus 4 plus 28, you get your 72. So if the condition, if $1 was equal to $3, then you would have worked on 72. Instead, the idea here is to proceed without jumping, right? So without, just go on to work on 40, 44, 40, 52. So obviously the question is, what if we are wrong and the branch is taken, right? So there are 2 possibilities, right? One is $1 equals $3. And if you assume that branch is not taken and start working on 44, if this is equal to this, then we are good, no problem. But if $1 doesn't equal $3, when you are working on this particular instruction, you have accidentally worked on 3 instructions. You would have had to just jump from here to there and worked on load word. So there should be a way for you to work around this problem. The workaround is, you have worked on all these, just flush them out of the pipeline. Whatever you have so far in terms of 44, 48 and 52, just flush them out. Make those 3 instructions NOPs. So go back and make all the control signals for those 3 instructions as zeros, so as to effectively not work on them. And I only need to worry about 3 of them, because you see this, when this guy is making the decision, one instruction is here, the other instruction is here, the other instruction is here. I only need to worry about 3 of them. So flush them out, change them to NOPs. That's going to be my one of the options. I need to do that for 3 of them. Now question is, how do you flush? As I said, just as you did for the NOP. Set all the control signals to 0 for 3 instructions. In our example, it is for AND, OR and ADD, because those guys are right now in the pipeline. And things have not really changed here, right? So instruction memory, you have read the instruction, you have read the register file, and then you have worked on the instruction for the first one. Second one, or the first one here, in the order, you have not really made much progress. You have not written to the register file. You have not written to the data memory. So by simply changing all the control lines to 0 for the 3 instructions that follow, you are effectively making them NOP, just like NOP. And now the instruction that follows is a load word instruction. So you are essentially making the decision here and then jumping to your next instruction, which is your load word. But because of that flushing, we would have lost certain cycles, and there should be a cost for that. So let's try to see the number of cycles lost due to flushing, what we call a branch penalty. Because if you make the incorrect decision, you have to track it back by flushing the pipeline, and hence you have to pay some branch penalty in terms of number of cycles. So let's try to find out what would be this branch penalty. The average cost of guessing branch not taken and being wrong is probability that the branch is taken multiplied by 3 cycles. Now, why is it 3 cycles? The probability that, because it matters for 3 instructions after that. In other words, that number 3 is coming based on when you make that decision in clock cycle 4 and the instruction that is just entering clock cycle 1. So that would be a difference of 3 clock cycles impacting the 3 instructions that follow branch when equal. That's why we are going to have to multiply that probability with 3. So how many cycles are you losing on average when you go wrong? Well, probability that the branch is taken multiplied by 3 will give you that result. You guys see that? Now, if the probability of the branch being taken is 0.4, just some arbitrary number there, then we have reduced the cost from 3 cycles to 1.2 cycles, right? So if you just plug in this 0.4 number over there, say 40% of the time you are taking the branch, then you have the branch penalty has gone down from 3 to 1.2. That is on average. If we could reduce the amount of time we spend doing this flushing, then we could lower this even further. And we'll see some ideas where we can do that. Reduce the penalty. Reduce the penalty essentially means make the decision earlier, right? So here is where we were making the decision, right? So this is where the branch decision was being made. After that ALU result was being matched with, are you branching or not? That was coming from the main control unit. So instead of making this decision that late, can I make that decision sometime earlier in the pipeline? If I'm able to make that decision earlier, then I may not need to wait until the memory access stage, the data memory access stage. And hence, I would have reduced the penalty. So for the branch, all I'm doing is checking the contents of two registers, whether they are equal or not. So in reality, I could have put a comparator right here whenever I read the register file for RS and RT. And if my comparator says that they are equal, I could have made that decision right there. So let's include a comparator. Soon after things are read out of the register file in the instruction decode stage. But for this, we would also have to move up the address calculation, because remember, we have to, the branch when equal needs to have an offset. That offset is a word offset, so you have to convert it into a byte offset by shifting left by 2, and you have to add that to hold up, this offset to the current PC, right? So PC plus 4 branch destination address equals PC plus 4 plus offset. So that offset is a word offset. I would need to multiply it by 4. So that's what is happening here, right? Let me use a different color. Sign extended. After that, you multiplied by 2, and then you took PC plus 4 from here and you added that. So soon after this adder, you have computed your branch destination, which was happening way later, right? So this was happening way later, right here. It was happening in the execute stage. Now we are also moving that up to the decode stage. So you are comparing in the decode stage, and you are doing that calculation of the branch address also in the decode stage. So you are able to move things up, which means that now you are going to not have that big of a difference, right? So instead of having things in stage 4, you are effectively evaluating things in stage 1. You have tremendously improved your branch penalty. You have reduced it by a lot. So if you are going to do a branch and the registers are equal, if the registers are equal, that means BEQ, you are actually taking the branch. All you need to do is set this field called flush in the IF, the instruction fetch stage, to be a 1. So here is your hazard detection unit. It is giving you, so here is your main control unit. The main control unit is going to check whether your registers are equal or not. And if they are equal, you are going to set the field IF flush to be a 1. If you set that IF equal 1 here, it is essentially going to flush out the pipeline that is only going to affect one instruction before. Does that increase the amount of time that the decode stage takes? Only by a little bit, right? But we are assuming that that is not going to significantly change it by much. So we are still assuming that it is negligible when it comes to 2 nanoseconds. So instead of doing this check of comparison and the branch evaluation here and here, we are doing it over here. And then if it actually means that we are doing a branch, we would just send a control signal to the IF pipeline register saying that you need to flush things out. So whatever is there, it is going to be flushed out, and you can come out of that incorrect decision very quickly. How is the condition being evaluated? It is right here. So the condition is being evaluated by looking at the comparator result. How is is the top left mux missing a signal? Top left mux. The top left mux, are you talking about this mux? That mux is only your PC, the address, right? What is the next PC source mux? So it's going to select between PC plus 4 plus offset and whatever your, so let's see, PC plus 4, right? So this is a PC source. So you would branch when comparator says equal and something else needs to happen, right? So the instruction has to be a branch, right? Branch control, branch equals 1. So there is a branch output that comes out of the main control line. That also has to be a 1. So there is a combinational logic component that is missing, essentially an AND gate that takes in an input of the comparator and one of the outputs of the control unit, goes through an AND gate and then feeds it back into the PC source. You see that? So this guy, where is the AND gate? Right here. That guy needs to take in 2 inputs, right? One input is ALU0, the other input is the branch, which the output of this guy goes into PC source. This is not shown in that. Instead of taking in the 0, it is now taking in the output of the comparator. All right, let's go on. All right, we talked about this. Comparator, flush it out. All right. So if our flush signal is 1, then we have essentially, that means that we change the fetch instruction to a NOP. And in MIPS, no operation is an instruction which has 32 zeros. All 32 are zeros. So it's actually the shift logical left $0, $0, $0. So it's actually saying do nothing to your 0 register, which anyway you couldn't write to anyway, right? So all zeros, all 32 zeros instruction is your NOP. Now let's try to see what are the benefits of the modified hardware. How much we have benefited in terms of our branch penalty. Whenever we are wrong, now it is going to be down to 1 cycle. Do you guys agree with that? Down to 1 cycle instead of 3 cycles. Down from 3 cycles. Earlier it was 3 cycles because CC4 minus CC1, right? CC4 was where you were making that decision, and CC1 was the clock cycle which was working on the most latest instruction, the third one in this case. And now we have changed it so that the decision is not made in CC4, it is actually being made in CC2, right? So CC2, and the next instruction obviously is CC1. So the difference over here is simply 1 as opposed to 3. So whenever we are wrong, the branch penalty is just down to 1 cycle, which means if I go back and take a look at my example here, the probability of branch taken multiplied by 3 cycles down, this number is 1 cycle. So for the same 40% probability that the branch is taken, I'm down to 0.4 cycles being lost on average. So that's a lot of improvement because we are able to make that decision early. All right, questions about these ideas? So stalling, all right, gives us the solution, but it's not really going to benefit in terms of time. So we have branch penalty. We can reduce branch penalty by trying to make that decision early in the pipeline, the second stage as opposed to the fourth stage. All right. Now let's try to go one step ahead, because there is also this probability of branch being taken and probability of branch being not taken, right? So let's try to see if we can actually predict the branches. And how would you predict? So if I ask you guys, on what basis would you base your prediction on, what would you guys say? You're trying to predict whether to work on the next instruction or the branch instruction. In other words, you're trying to predict the branch is going to be taken or the branch is not going to be taken. So what would you base this prediction on? A condition. So probability. Yeah. So okay. So here, let me ask you this again. Whenever you are asked to predict the future, what kind of information would you look for in order to make a better prediction? Previous outcomes, absolutely, right? So previous history. So you would try to look at the history, and based on the history, you would be able to predict. And even then, you may be wrong, but that's your that's the best way possible. So our predictions are going to be based on the past, the history. So prediction, again, where you can predict two things. One is branch is going to be taken or branch is not going to be taken. And if branch is taken, then your program counter will be updated to PC plus 4 plus sign extended offset multiplied by 4. This 4 is to convert a word offset into a byte offset and then add everything else, right? So that would be your new program counter. That's when branch is going to be taken. When branch is not taken, you simply work on the instruction that just follows the branch instruction, which is PC equals PC plus 4. So those are the only two possibilities, and you have to predict which one. Now, whenever you predict, you would want to go right, but sometimes you may be wrong. So if you do a correct prediction, what is the impact? And when you do an incorrect prediction, what is the impact? So if you do a correct prediction, we have no branch penalty because you did it right. And branch when equal takes just one cycle like other instructions. You are going through the branch when equal instruction, and soon after that you have predicted it correctly. You don't have to waste any time. No branch penalty here. However, if you make that prediction incorrect, you would need to flush the pipeline. Branch when equal is going to take one extra clock cycle because you have added one more clock cycle to that instead of 3. This is assuming the modified hardware. So I think the price to pay is need to flush the pipeline, and the branch when equal takes one extra cycle. Now, as I said, prediction should be based on history, and it should also be based on some facts, right? So let's take a look at a couple of facts here that are sort of general. Branch when equal instructions, when they appear in loops, those branches are taken often. So if you write a for loop or a while loop, if you are writing a while loop and checking for two things equal or not, those branches are taken often, right? Whenever it breaks, that's when you come out of the loop. So this is fact number one. On average, branch when equals in loops are taken often. Branch is taken often. Over here, the second fact is branch when equal instructions for testing rare cases are rarely taken. So for the case of, say, errors, those cases that are testing for rare scenarios like errors are rarely going to be taken. So these two facts can actually bias our predictor. Now the idea is have two versions of branch when equal with different opcodes. Version 1 of the branch when equal assumes that branch is going to be taken, and version 2 is going to assume that branch is not going to be taken always, right? So now you have two versions of the same instruction, one relying on more branches being taken, one relying on more branches not being taken. So separate opcodes. Or a better way of doing this is dynamic prediction. You are changing things as the instructions are getting executed. You are predicting whether the branch is going to be taken or not taken as the instruction, as your program gets executed. And you can do this by keeping a history table of all the branch instructions. You can monitor whether the branches have been taken so far or not. And you can make the prediction based upon that history for that particular instruction. It would be ideal to change something if it breaks twice as opposed to just one wrong prediction, right? So if 99% of the time you are taking the branches and just once you got a branch not taken, then it is not sensible to change your whole process because of that one incorrect event, right? So what the better way to do that is prediction must be wrong twice for you to actually change the type of prediction you're making. So if you're saying let's take the branch, let's take the branch, let's take the branch, you have to be wrong twice, meaning two branches have not to be taken, so that now you can go to that branch not taken state. All of this can be expressed using this state diagram. So all the way to the top left, you are in a state where you are predicting that the branch is going to be taken. So if you are in this particular state and your new inputs are branch is taken and branch is taken and branch is taken, as long as the branch you keep taking the branch, then you can stay in that state. But for you to go into that predict that branch is not going to be taken, you need two incorrect predictions. One not taken, the other not taken. So two incorrect predictions will land you in this new state called predict not taken. So when you are in this state, then you can start predicting that the branch is not going to be taken. And if you continue to get not taken, you stay there, right? So these are states. Now, if you are in a state in which you are predicting that the branch is not going to be taken, you would need two branches to be taken to change that to predict taken, right? So you can think of it as, say, this is S0, S1, These are states, right? In order for you to go from S0 to S2, you need two not takens to actually happen, two incorrect predictions to happen. Then you can go change your scheme. If you are in S2 to go back to S0, you need two incorrect decisions of branch being taken. And if you follow this, amazingly, you are able to achieve 90% accuracy with this scheme. So this starts at S0, right? So we are assuming wherever it starts, right? So it could start in either the version 1 or it can be version 2. So depending on what the assumption is, it has to be assumed that you are starting off with it has to be explicitly mentioned that you have to base it out of some starting point. But for our discussion, we are assuming the way I have numbered, I'm saying S0 is the state where things are starting. But for some other scenario, you could start with this one. But the point is that two incorrect events that actually happen will change your prediction for the next one. Other questions about this? All right. Now let's talk about rearranging the code. Now, whenever you do a delayed branch, you always execute the following instruction. We have talked about the modified hardware going as far as affecting the next instruction. So the next instruction always gets executed, but the instruction following that will be affected by the branch. So that's one thing to note. The delayed branch always executes the next instruction. The following always executes the following instruction. But the instruction that follows that can get affected by the branch. So it may or may not get executed. The compiler is going to rearrange the code so that the next instruction is always executed. That location is called the branch delay slot. So the instruction that follows the branch statement is called the branch delay slot. That is when that is where things in the branch delay slot are always executed. No matter whether you are taking the branch or not taking the branch, they will get executed. The compiler tries to put a useful instruction after the branch that will be executed in either case. Because I want to benefit from that. That is going to always be executed. So why not use it for an instruction that helps my program move forward? Now the code rearrangement does not alter the result, right? I cannot rearrange the code to alter the result of my program. I have to stay consistent with that. And if I cannot put something useful in there, I can put a not instruction in there. So let's take a look at some examples. I have 3 examples here where I am putting something useful in the delay slot. So I have a add instruction here. Then I have a condition which could be, something like branch when equal $1 $S2. What is S2? S2 comma $0, right? Comma whatever offset. So I have an add instruction followed by a branch instruction followed by a delay slot which always is going to get executed. What follows the delay slot may or may not get executed depending on the branching, but this will get executed. So how can I change this code a little bit? Well, if I put this add instruction in the delay slot, then I'm using it for a good purpose, right? So you see this, I take the add instruction, I'm using S1, S2, S3 here, and I'm just putting it right here. Can I do that without any problem? I'm able to do that because S1 is the destination. S2 is not the destination. If S2 would have been the destination, then I may be in a problem. But S2 is not the destination here for the add instruction. So I can go into the loop, then I can bring in the add over here because it doesn't matter. So I'm now using the delay slot for a useful purpose. That was part of the instruction, right? So this is called working on the instruction from before the condition, right? So from before the condition was here, you are working on the instruction before it. And you can do this since the add instruction does not depend on the branch, and this is the best way when it is possible. This works out really well. The second example is get the instruction from the target. So you see this, you have a subtract instruction somewhere, you have an add instruction here. In this case, you are writing to S1 and you are immediately checking for S1 is 0 or not. Following the branch instruction, you have that delay slot that could be executed. Now, in example B, we are looking at a situation where we cannot move add because you see this branching depends on S1. So I cannot put it below the if. The only thing that I can do here is from the target. The target of the branch instruction is the subtract instruction. That subtract instruction can be moved into the delay slot, which is going to be executed. So moving the branch destination into the delay slot helps you use that delay slot in a meaningful manner. Like you're using it for an actual instruction in your program. You guys see this? Questions here? There is one more example in example C. Isn't the intention of the subtract instruction for it to be run multiple times because of the loop? Well, you are so this is one particular destination, right? So you're assuming you're not see if the branch is taken or it's not taken, the subtract instruction is going to get worked on, right? Because it is sort of part of the if condition almost. They are linked together if they are going into the pipeline. So two things can happen, right? This could go to 0 or it could not go to 0. If it goes to 0, if the branch gets taken, then this guy gets worked on. And if the branch doesn't get taken, this gets worked on, which was happening over here anyway. All right, the third example here is look at it from the fall through. So again, you have an add instruction followed by a branch, followed by a delay, and at the end of that branching destination, you have a subtract instruction. So here you can take this fall through instruction and move that up into the delay slot. So you still do the add, can't move that into the branch slot, then you still check, and now you are putting this subtract instruction over here, which you are working on, and this is pointing to the other instruction, where an updated branch destination. You can have something else over there. Now this one will work if the subtract instruction can be executed for both outcomes, right? If it doesn't, then we have a problem. So the three examples, one was from before the branching, one was from the target, whatever the target is, move that into the delay slot, and the last one is from the fall through, the last instruction, whatever that if statement is, if it is going below, take that and put that in your loop, right? So the last instruction in your if condition. All right. This is all I have for you guys. We have a few minutes left. I encourage you guys to now start working on the activity.